We have a circuit here, and this consists of a cell and a switch and a capacitor. The cell is of EMF E, capacitance is C. We close the switch at some moment. Initially the capacitor is uncharged. When you close the switch, charge builds up on the capacitor, and we have not shown any resistance explicitly here, but there would be resistance in the wires. Well, so charge would flow onto the capacitor plates, and well, as the charge adds up here, negative and positive charge will be induced on the plate here, and the positive charge goes back to the circuit. So the cell circulates charges. Initially the charging rate will be high because there is no charge here to oppose the inflow, and as the charge builds up here, the inflow will be opposed, and when this and potential difference becomes equal to the potential of difference of the EMF equal to EMF of the cell, the charging stops. You will learn later on that it takes infinite time to have this build up, but then that's theoretically. Well, 99.99% of build up will be over in a few milliseconds, depending upon the values of resistance and capacitance. So for all practical purposes, very quickly this capacitor acquires its charge. And when will the charging stop? When the potential difference across the capacitor is equal to the EMF of the cell. Now when that happens, the energy stored by the capacitor, electrostatic potential, will be half C squared. Potential difference is Z, right? And the charge and that will be potential difference is E, so capacitance C, so this is CE. Now work done by the cell in building up this charge is, what is EMF E? The work done per unit charge as it is circulated by this cell. It's circulated charge of Q, so work done by this cell would be E into CE is CE squared. So work done by the cell is CE squared, electrostatic potential is stored in the capacitor is half CE squared, the rest is heat. Well, as the charge flows to the wires, heat will be evolved, and you can see that half the work done by the cell is wasted as heat in the circuit. It's a big waste, right? 50% of the energy is lost here, only 50% of the work done is useful energy in the capacitor. So where is this heat evolved? In the circuit, in the resistances that are in this circuit. We haven't shown them explicitly, but you'll learn about this later on. You can in fact also work out the heat evolved in a different way by looking at the current in the circuit as a function of time and all that. You will do that later. We now have a circuit with two capacitors C1 and C2 and a cell of EMF E. This is a special kind of a switch. It's called one pole two-way. In the sense, flow connections can be made this way, that is C1 could be connected to either the cell, or when you throw the switch this way, well, it's connected to C2. This throw is not physically throwing something at somebody. It is the way you use language. There is a switch here which can be pushed to the terminal 2, so that's typically called throwing. And initially this is the condition, so this capacitor C1 would have been charged to E volt. The potential difference of the capacitor will be same as the EMF of the cell, and so it will have a charge Q of Q1, let's say, or Q, and this will have no charge, right? This are not connected. This is charge Q of C1E here, and that's it. There's nothing more to learn there. In the process of building up of this charge, some heat would have been produced in this circuit and all that. Our interest is what happens when it is thrown to switch this way to connect to, so that this capacitor discharges, loses some of its charge to the capacitor C2. So some charge will flow here from here to C2, from this plate to this plate, and as charge arrives here on the top plate, it will induce a negative charge and some positive flows back. So this part of the circuit is active when you throw the switch to 2. And at the end, when eventually you have charge flow is stopped in the circuit, we could do something like this. Well, the potential here, if we assume as 0, earlier when it was connected this way, it was E, right? This was E. Now, let's call that some V1. Potential is V1. So, the top plates of both the capacitor potential V1 when charge flow is stopped. Now, what you do know is that the charge on this will be C1 V1 and this will be C2 V1. And this charge must be, well, the total amount of charge doesn't change, right? So you have the charge here is C1 V1 and the charge is C2 V2, and that must be equal to the charge Q earlier you built up. So C1E equals C1 V1 plus C2 V1. So that allows us to solve for V1, and V1 equals C1E by C1 plus C2. And then you have some other calculation that you can do, like for example, what is the energy of the first capacitor? What is the energy of the system of capacitors? U is, this would be UF, let's call this, of the system of capacitors, half C1 V1 squared, and then half C2 V1 squared. So half C1 plus C2 into V1 squared, that's V1, is this C1E by C1 plus C2 whole squared. So this is C1 squared E squared by 2 C1 plus C2. This is the final energy of the capacitor system. And what was the initial energy? Half C1 E squared. UI is half C1 E squared on this capacitor. There is no energy there because it is an uncharged capacitor. So this is it. So there is no cell here doing any work, and so you have a difference between these two will be the heat evolved in this circuit. Its final energy would be lower than initial energy, and some heat would have evolved in the circuit. So in fact, what is the heat evolved if you want? Loss in potential energy, UI minus UF, that's the loss. And delta U would be change in potential energy of the system, but we're looking at minus delta U, the loss, which is UI minus UF, half C1 E squared minus half C1 squared E squared by C1 plus C2. You can work this out, and whatever you get is the heat evolved in the circuit. Invariably, heat is evolved when the charge flows through these wires. So it's like a charged capacitor and then connect it to another capacitor. The switching does that. You charge the capacitor C1 and then you kind of disconnect it from the cell and then connect it to the other capacitor. So in the process of that connection, as the charge flows through the wires, heat will be evolved, and our interest is to find how much heat is produced in the circuit when the switch is thrown from 1 to 2. You can simplify this. It's not too much of work, I guess. This is 2 into C1 plus C2, and then the denominator, and then this is C1 squared, multiply this, C1 squared plus C1 C2, C1 squared plus C1 C2, plus there is minus C1 squared. So it is C1 C2 by into E squared, of course, into E squared. So that is C1 C2 by 2 into C1 C plus C2 into E squared. It would have been a little easier if you made the capacitor C and C, and that would have given you a very simple result. So heat is invariably produced when the charge redistributes in the circuit. Our interest is to find how much heat is produced. We have a circuit like this. Well, our interest is to find what happens when the switch is closed, how much heat is produced in the circuit. For convenience, we've used values of 3C and 6C to make it easy for us. And well, the initial state is simple. This capacitor charged to the cell of EMF E, and you want to find the initial state. How much charge do they have? What are their potential differences? Capacitors is a given, right? So what can we find? What are the charges on the capacitors? What are their potential differences? We don't need a serious calculation for that. Just the fact that these are in series, 6C and 3C. There is no junction here. There is no. This path is open. So 3C and 6C are in series. That gives us an equivalent capacitance of 2C, and the potential difference across that 2C is E. That is the potential difference across the combination, which is the same as across the equivalent capacitors. So charge on the equivalent capacitor will be 2C into E. So, and the charge in the equivalent capacitor and the individual capacitors will be same in series combination. So this charge is 2CE, and this is 2CE. That is the initial state. If you wanted the potential difference across individual capacitors, this E will divide in the inverse ratio of capacitances. So in the ratio 3C is to 60, that is 2 is to 1. Sorry, 1 is to 2. 3 is to inverse ratio. So E dividing in the ratio 1 is to 2. So E by 3 and 2E by 3. Across 6C it will be E by 3. So this mark is this is 0. This will be E by 3. That is the initial potential. If you wanted that. Since potential is E by 3 and charge the capacitance is 6C. 6C into E by 3, that will give us the charge 2C. Same thing here. This is 2E by 3. This is 0. So this is E. This plate is at E volt. This is E by 3. So that's 2E by 3 into 3C. That comes to 2CE. So we got everything that we need to know. So the charge in the plates is 2CE. I marked it here. And we know the energy of the system UI, let's call this, of the system of capacitors, that is half 2C into E squared. The energy stored in the equivalent capacitor, which will be same as across the individual capacitors. Some of the charge energy stored in the individual capacitors. You can work that out. When you close the switch, things change. Like the potential difference will change. This will change from this 0, so this will be E volt, right? So this will change from E by 3 to E. This is 0 and this will remain E, of course. The cells are capable of maintaining that potential difference, right? The cells maintain that potential difference. 0 along this path, it will be E here. This is closed, E. So E by 3 changes to E. This 0, this anyway was E. So this is E and this E, the charge stored in this capacitor would be 0. Potential difference is 0. Which would mean that that charge 2C flows through the battery like this. Right? And what about this? If this is E and this is 6C, the charge here will be 6CE. Right? The potential difference across 6C will become E, 0, and this closed, so this is E. So this charge will change from this is 2CE to 0, and this is 2CE to 6CE. There is a change. In fact, a 2CE would have flown like this to come to the junction. And well, let's find out the charge that flows through this path. Well, some of the charge earlier in this was 0, right? Why 0? Well, these are connected internally. Well, this is the connection that we had, no connection here. So that was induced charge, that was 0. This is minus 2C, this is plus 2C, so that's 0. Now this is 0, 0, and this is 6C. So 6C is flown this way, right? Whatever charge is flown here this way, 6C, of that 2C goes this way and neutralizes this, and 4C comes this way and adds up to this 2C already present. So 6C is flown here this way, of that 2C has gone this way to neutralize this, and this is 4C that's come this way to add up to 6C. And so we know everything that we need to know. So work done by this cell on the left side, WL, let's call that. Charge is flown this way, so that's how much? 6C into E, that's the work done by this cell. And what is the work done by the other cell on the right side? This is after the switch is closed. This is charge 2C flowing towards the positive terminal, right? So negative work is done here. So minus 2Ce into E. Work is done on the cell and by the system. So charge is flowing into the positive terminal here. This is 6Ce this way and this is 2Ce this way. We have initial energy here. How about final energy? The final energy of the system of capacitors is, this is no energy, no charge on this. And this is half 6C into E squared, potential difference Z, right? Half 6C into E squared. That's the final energy. So what is the heat evolved? Now, heat evolved is, well, the energy increase must be equal to work done, but if work done is greater than the energy increase, the remaining is the heat. So, in fact, let's find the well, change in potential energy here. How much energy is changed there? This is half 2C squared. This is half 6E squared plus nothing on this, right? 0. This is the energy of the two of them together. We got that by replacing these two by an equivalent capacitor 2C. So this is the delta U of the system. Delta U is final minus initial, half 4C into E squared. And heat evolved will be, that's 2C squared. And heat evolved, the potential energy must have increased by an amount equal to work done, but something is lost there. So all the work done will not be equal to potential energy increase. So that will be 2C squared, and here you can see this is work done is what? 6C squared, and this is minus 2C squared. So work done is 4C squared. This is 2C squared. Excuse my bad handwriting there. This minus 2E, this is 2C into E, right? Minus 2C squared. That's 4C squared. If I add these two, work done by the cells 4C squared. Work done is 4C squared, but energy increase is only 2C squared. So heat evolved is 2C squared. This is the heat evolved. Work done minus potential energy increase. If work done is equal to potential energy increase, there will be no heat evolved. But work done will be always more than potential energy increase, because some amount of it will be heat. This is work done minus delta U of the system. So this is what we have calculated here, right? This is what we have calculated here. And well, that's it. I'll find the initial state, find the final state. Somebody asks you how much is heat evolved. So you say 2C squared is the heat evolved. We have a circuit here, and our interest is to find the heat evolved in this circuit, that when the switch is closed, and the charge that flows along the paths 1, 2 and 3 after the switch is closed. The initial state is again simple. 3 and 6 are in series, so there's no junction here, and since there's no path here, it's open. So 3 and 6, 2 microfarad, and then potential difference across them is 12 volts. So if you call this, say, 0 volt here as a reference value, this will be 6 volt, and this will be 12 volt, and that will be 12 volt. So potential difference across the combination is 12 volt. If you want to find the individual potential difference, that 12 volts divides the ratio 6:3, that is 2:1. So across 3 microfarad it will be 8 volt, across 6 microfarad it will be 4 volt. So this is actually 4 volt here. Since this is 12, this potential difference is 8 volt. That is the initial state. And the charge on the capacitor, this is equivalent capacitor of 2 microfarad. So 2 into 12, right? That's the initial charge. Let's call that Q. That Q would be initial charge, and this would be 2 into, well, there's 6, 12 volt, that is 2 into 12, 24 microcoulomb. That is here. That, let's call this Q, and Q, that will be 24 microcoulomb. What is the initial energy? Qi, half CV squared, half C of the equivalent capacitor, that is 2 microfarad, into 12 squared, half C squared, 12 squared, that is 144. 144, this is 2 microfarad, and 144, so this is this many microjoule. This is 2 microfarad, right? So that's it. that is 144 microjoule. We know the initial state. Now when you close the switch, this 0 volt, this 6 volt, and this becomes 6 volt because you connected 6 microfarad in parallel with the 6 volt capacitor and cell, and 3 microfarad across 6 volt. And when you close the switch, this is in parallel with this, that is, it gets a potential difference of 3 volt. This potential changed from 3 to 6, so it will remain 12, so 6 and 12, so this 0 and 6, because of the changes in potential difference. Now what are the changes in charges? This, if this 6 volt, this will become 36 microcoulombs, so let's call that Q1, Q2, and this Q1. So Q1 would be, the charge Q1 would be, that is 6 volt, so 6 into 3, 18 microcoulomb. And this will be 36 microcoulombs, right? Q2 would be 36 microcoulomb, 6 into 6, right? This potential will be 6 volt, 36 microcoulomb. And so we can find the charges that flow along various paths here. This was earlier 24 microcoulombs, now it is 18 microcoulombs. So 6 microcoulombs is flown this way, right? This was earlier Q was this 24 microcoulomb, now Q1 18 microcoulomb. So 6 microcoulombs is flown this way. So this is 6 microcoulomb along path 1. And how about 3? This was earlier minus 24 microcoulomb, now it has become minus 36 microcoulomb. Right, minus 24 to minus 36. So 12 microcoulombs is left. So this way 12 microcoulombs is flown, right? Minus 24 to minus 36. So the charge that is left is 12 microcoulomb. So this 12 microcoulomb and the 6 microcoulomb, 6 coming this way, 12 coming this way, and what goes to be 18 microcoulomb. This way will have 18 microcoulomb in this path. And we can also get that by looking at the charges on these two together. Initial charge on these two together was 0, right? This is no connection like this, so charge on these two together was earlier 0. This is minus 24, this is plus 24. And now this charge is, minus 18 microcoulomb and this plus 36. So total is become 18 microcoulomb. So 18 must have flown this way. We can get that this way too. So 12 coming this way, 6 coming this way, flowing as 18, we can get that either way. And what is the final energy of the system? Energy of the system finally UF is across that half 3 into 6 squared, 36, 18, so half, let's put that this way, half into 3 microfarad into potential difference is 6, 36, 6 squared. This many microjoule, of course. So this is plus the other one, half 6 into 36 squared. This will be so many microjoule. So this will be, how much will this be? This is 18 into 3, 54, 54, and then this is 108, 54 plus 108 is 162, right? This is 162 microjoule. And this is UF. And what is the work done by these cells? So this is the first cell and the second cell. The work done by the first cell. Charge is flowing this way, right? And opposite the sense of EMF here. So this work is minus 36 microjoule. Right? 6 is flown into the terminal here. Whereas this way, 12 is flown this way, 12. So that W2 will be 12 flown away from the positive terminal, so charge flows this way, right? The circulation is this way, 12 into 6, 72 microjoule. That's work done by the second cell. So you can find the heat evolved as work done, the sum of these two, that is 36 microjoule, and delta U, change in potential energy. Final is 162, initial is 20, this is 144, 166, 162. So you get a difference of 18 microjoule. There is an increase of 18 microjoule. So you can find the heat evolved as work done minus change in potential energy, which is 18 microjoule. So this is 18 microjoule of heat is evolved in the circuit. Not too much of work, and but this is what it is.